let's get started with the microcontroller and embedded system lab today. So before understanding how to write a program, we should know what are the instruction set, how to write a small code fragment, and how to execute what type of IDE is required, and how do you create a project. What is the editing tool, what is the debugger tool, what is the compiler that is required, or the assembler tool that is required. How do you actually compile it and get the object file. So what do you mean by hex file? So all these concepts you have to understand before executing a program. And hope all of you have laptops with you, and I want all of you to install a software called as Keil, Keil. So I will just write it here. So subject code is 18 CSL 48. The lab name is Microcontroller and Embedded System Laboratory. So this is your CIE marks. It's evaluated for 40 internal assessment marks, and the SCE examination, even though you write it for 100 marks, it will be scaled down to 60. And the total number of lab contact hours is 36, exam hours is 3 hours, as you know. And if we go through the syllabus, lab cycle syllabus, there are basically two parts, part A and part B. Part A is all about software programs. So you just have to write a ARM assembly program and execute it using Keil environment. So what is that Keil? Keil is an IDE. Keil is a tool or IDE, integrated development environment, where you have everything in it: editor, assembler, compiler, debugger, whatever is required for executing your ARM assembly program. Everything is available in the Keil IDE. So the spelling goes like this: Keil. So this is Keil. Microvision 4 and above. So I think it's freely downloadable. You try downloading this Keil Microvision 4 IDE, install it into your laptops. You can work, you can execute any program, but only part A programs. Part B programs, you can just compile it, and for seeing the result, you need to interface the hardware. So you need a controller evaluation board like this, ARM7TDMI/LPC2148 evaluation board, so which cannot be done using online. So it has to be done in the offline mode, because you cannot purchase the board individually. It has to be executed in the college. We have the development boards, and once you are, hopefully by the time I complete the software programs, you will come to college. You the classes, let us hope that the classes will be in the offline mode, so that it will be very helpful for us to see how actually the hardware programs can be executed, right? So part A, if we go through the syllabus, part A has 8 programs. Actually, there are 16 programs, including part A and part B. So part A consists of 8 programs, and part B is the rest of the 8 programs. So what is that you are going to do using, what is that you are doing in part A programs? So first one is write a program to multiply two 16-bit binary numbers. So it's a very straightforward program. You need not scratch your head too much to understand and execute this program. You get two numbers into two general purpose registers, but they have to be 16-bit numbers. But whatever register size is available is all 32 bits in ARM. So how do you actually load a 16-bit number? So we'll see that. And how do you do the multiplication operation on those 16-bit binary numbers? So, so there is a mul instruction, as you know. In any sophisticated processor, you have an instruction called as mul, multiply, for multiplying two integers, right? So that's how you multiply two numbers. But after multiplying, I don't want the result to be stored in the register, in a destination register. I want the resultant to be stored in some memory location. So for that, we make use of the store instruction. Whenever I multiply two binary numbers, two 16-bit binary numbers, the whatever result we get will be twice the size of the operands. Multiplicand and multiplier are 16 bits, but when you multiply two 16-bit binary numbers, you get a 32-bit result. So that 32-bit result, anyway, your register size is also 32-bit. That will be stored in the destination register, which is 32 bits in length. Now I want the resultant to be stored in memory location. So we basically make use of the only way we can store the resultant in memory location is by making use of store instruction. So what type of architecture is this? Can anyone tell me what is the architecture? Whenever you are using load and store instruction to access memory, so what is this architecture called as? I have also discussed this in the theory class also. Anyone from the class? I want this class to be very, very interactive because it's a lab session. You have to be carefully follow the steps that is discussed here and try to execute whatever programs we have in the lab cycle, as well as some simple programs, very simple programs, so that you will get an idea of how the ARM assembly programs gets executed in the Keel environment. Similarly, I may give you some assignment, some extra programs to execute, which is just almost similar to the lab cycle programs. So I want you to try all these in your laptops by loading and installing the Keel software. So I will just demonstrate today. And by next week, I want all of you to install this Keel software, which is freely downloadable. It's Keel Microvision 4. Right. So when I was talking about the load and store instruction, the only way in RISC architecture to access the memory is by making use of the load and store instruction. So that's why this architecture is also called as load store architecture. So load is accessing the operands that is stored in the memory, getting it to one of the general purpose registers. It could be to multiple registers as well. There are instructions. There is a single instruction to load multiple registers. We'll be talking about that later. So since the only way with which we can access the memory is through load and store instruction, this architecture is also called as load store architecture, and all the RISC architecture uses the Harvard architecture. That means to say it has a separate data memory and a separate instruction memory. Right. So once we have multiplied those two numbers, 16-bit binary numbers, as I told you, the result will be twice the size of the operands. So anyway, that will be in a 32-bit register. As you know, all the registers available in ARM are 32 bits in length. So they will be available in, they will be stored in one of the destination registers. And what we have to do is we have to make use of the store instruction to store the resultant into some memory location. So that is the way that is the algorithm that is used to multiply two 16-bit binary numbers. Similarly, I have second program which is used to find the sum of first 10 integer numbers. So these first 10 integer numbers, 1 plus 2 plus 3 plus 4 etc. up till 10. So you have to add and store the resultant in again memory location. So what is that you have to do? First initialize first number, that is 1, into some register. Keep on incrementing that value. Add that incremented value to the already added register contents, and check final 10. If it is greater than 10, you stop adding the numbers. Otherwise, you keep on adding after incrementing the number by 1. So finally, after all the 10 numbers are added, the resultant will be again in a third destination register. So what you are supposed to do is you have to get that result from the destination register, transfer it into memory location. So this basically uses the looping instructions. We'll see how looping instructions can be used. And the third program is write a program to find the factorial of a number. So for finding the factorial of a number, you can use different ways. Either you load the number into two different registers. One register you keep decrementing the value. Check whether the value that you have decremented has reached 0. If it is not reached 0, then decremented value you multiplied with the original number. So like that you repeatedly do the operation until the decremented value becomes 0. So you have the resultant in the destination registers, so that if you're interested, you can store the factorial of the number which is in a register to memory location. So this is the third program. And the fourth program is to add an array of 16-bit numbers and store that 32-bit result in internal RAM. So this they have specifically asked you to store the result in the memory location. So array of 16-bit numbers. So you can take any number of elements. So they have not specified how many numbers you are supposed to add. Add an array means you can take 2 numbers, add it. That also becomes an array of 2 elements. Add it and store the resultant in the memory location. Next one is fifth program is to find the square of a number using lookup table. We'll see what exactly is this lookup table and what is actually stored in the lookup table. How do you extract the square of the number using the lookup table method? Sixth program is write a program to find the largest or smallest number in an array of 32-bit numbers. So once you write the largest number program, it's very simple to modify so that you can find the smallest number in an array of 32 numbers. So this is also you have to make use of the looping instructions, because you have to repeatedly keep checking whether the current number is greater than the next number or lesser than or equal to the next number. So like that you have to repeatedly keep checking the number until you have got the largest or the smallest number. So that is the sixth program. And the seventh program is to write a program to arrange a series of 32-bit numbers in ascending or descending order. So ascending or descending order, they have not specified what type of sorting method you are supposed to use. So we'll keep it very simple. Let us make use of the bubble sort algorithm to sort numbers, unsorted array of 32-bit numbers. So once you know how to write a program to sort using ascending order, using bubble sort, in ascending order using bubble sort, so there is a slight modification to the program so that you can modify it to make it work to arrange the numbers in descending order as well. So there is the seventh program. Eighth program is to write a program to count the number of ones and zeros in 2 consecutive memory locations. So to check the number of ones and zeros in 2 consecutive memory locations, so how do you do that? You have to move every bit in 2 consecutive memory locations, right from the LS bit to the MS bit. Every time you move the bit to the carry flag, check whether the carry is set. If carry flag is set, then you increment the ones counter. If it is reset, you increment the zeros counter. So you will be basically having 2 counters. One is zeros counter and the other one is ones counter. So depending on carry flag set or reset, you are incrementing either of the 2 counters. If carry flag is set, increment the ones counter. The carry flag is reset, increment the zeros counter. So this operation has to be repeatedly done until all the bits, right from the LS bit to the MS bit, is moved to the carry flag one by one. So that is by making use of the logical instructions, rotate instructions, rotate the data towards right through carry. So that is how write the program. So these are the 8 software programs. So that has to be written in ARM assembly language. So these are assembly programs, and ARM LPC 2148 is nothing but version of processor, one version of processor which is manufactured by Philips. So we'll see while executing how to select this LPC2148. So in part B, you are supposed to use the evaluation board. There is a board called as ARM70DMI/LPC2148 evaluation board. Whatever programs you are writing in part B is basically embedded C. So you are not writing the program in assembly language. You are writing in embedded C. Since you know how to write a C program, it is not very difficult to understand how to write an embedded C program. But you need to understand some of the basic concepts because you are interfacing the peripheral devices like UART, DC motor, stepper motor, ADC, DAC, keypad, and LED, 7-segment display. So all these are used for in communicating with the processor. So what is that you are going to do in part B? In part B, so in part B, first is you are supposed to, there is in the development board itself or in the evaluation board itself, you have this UART, internal UART means it's available in the same evaluation board. Need not externally interface this universal asynchronous receiver transmitter device so that you are able to display the hello world message on this UART. So it's available internally on the same evaluation board. So just that you need to know what are the ports that are used, what are the output ports that are used, and what are the general purpose IO pins. They are called as GPIO pins, general purpose IO pins that are supposed to be configured so that you are able to transfer this hello world message on the internal UART using the internal UART, and it will get displayed on the 7-segment. It will get displayed on the LCD display. That LCD display is also available in the same UART, same evaluation board. Sorry. And the next one is how to interface and control a DC motor. So there are many interesting projects that can be done using ARM. You can interface, you can actually control a DC motor, interface a DC motor to the ARM7TDMI or LPC2148 evaluation board. You can control the rotation. Speed of the DC motor can be controlled, direction in which the DC motor is rotating can be controlled. So that is possible, which can be this DC motor which is used in various applications. So that is how you control your peripheral devices through your programs. Embedded C programs. They are all embedded C programs. So the third program is interface a stepper motor and rotate it in clockwise and anti-clockwise direction. So there is one more type of motor called a stepper motor, which is a unique type of motor that is to be interfaced to the evaluation board. You are supposed to write a program which will make the stepper motor rotate in both the directions, clockwise and anti-clockwise direction. You can as well you can as well control the speed of the stepper motor also, right? So this is the third program in part B. Next one is determine digital output for a given analog input using internal ADC of ARM controller. So there is an internal analog to digital converter available. Similarly, you have a DAC program, so digital to analog converter, that you are supposed to interface to the evaluation board and generate triangular and square waveforms. So given the digital data, how it actually converts it into analog form and generates these kind of waveforms. Not only triangular or square waveform, you can also generate sinusoidal waveforms also. So any type of waveform can be generated once you interface a digital to analog converter to the evaluation board, LPC2148 evaluation board. And suppose I have an analog input given to internal ADC, how that ADC converts it into digital output. So that has to be determined. So you have to write a program where the internal ADC, given the analog input, how it actually converts it into digital output. So whatever digital output that you are getting, you should be able to display it on the LCD display. There is an LCD display on the interface circuit itself, or in the evaluation board itself. So you are supposed to display the equivalent digital output that you get from the ADC as the output, which is to be displayed on the LCD display. Similarly, I am supposed to interface a 4x4 keypad. 4x4 means it has 4 rows and 4 columns. So whatever 4x4 keyboard you are interfacing, suppose if I press a key on the keyboard, what key you have pressed, that should be displayed on the LCD display. So suppose if I press the key as 0, so 0 should be displayed on the LCD display. So you have to basically control this keyboard, or write a program which controls this keyboard, and whatever key that I have pressed, it has to sense the key that I have pressed and display the key code on the LCD display. So this is also an inbuilt, there is also an inbuilt LCD, which is basically a 16x2. So it has, actually it is a 2x16. It has 2 rows and 16 columns. 2x16 LCD display. And next one is, if I write a program, I can write a program so that the LED can be turned on and off at regular intervals of time. So by making use of the external interrupt, I can make the LED on and off. So that is another program. So this is again LEDs inbuilt into the ARM evaluation board. And the last is how to display the digits 0 to F on a 7-segment LED interface with an appropriate delay in between. So you have an LED interface available on the ARM 70DMI/LPC2148 evaluation board. So that you have to write a program so that you will be able to convert that hex digits to its equivalent 7-segment code, and that 7-segment code has to be sent to the display device, which is basically a 7-segment LED interface device, so that it displays these digits 0, 1, 2, etc. up till F. These are all hex digits. So that is one application of this is you have 7-segment displays on most of the home appliances. So you take, for example, your home appliances, appliance like a microwave oven or a washing machine, or if you consider a digital clock also, it has an LED 7-segment display in it. So you are supposed to display 0 to F on the 7-segment display one by one. In between, you have to give certain delay so that the user will be able to distinguish between the different count values. So that these are the programs that are available, that are to be executed, part A and part B. So you are supposed to execute one program from part A and one program from part B in the external examination. Similarly, in the internal assessment also, you are supposed to execute a program from part A and program from part B. And this is how the lab marks gets distributed for the practical examination. So since you are doing it, since you have both part A and part B, procedure, execution and viva for part A is 6 plus 28 plus 6. So part A will be evaluated only for 40 marks. Part B, the remaining 60 marks is allocated for part B. And the split up is like this: procedure 9 marks, execution 42 marks, and viva is 9 marks. So if you are successfully able to execute part A and part B programs, and if you do well in your viva and write up is very neat, if your handwriting is legible, and if you have not made any mistakes while writing the programs along with the interfacing diagrams, probably you can expect 100 out of 100 in the external examination, as well as full marks in the internal assessment also. So this is what I wanted to discuss regarding the lab programs. So these are the programs that you are supposed to execute. Now, so before going to the details of how what are the ARM instructions that are available to execute these programs, so let us see what are the objectives, what are the course outcomes for this course. that is laboratory course. So let us not worry about the mapping, program outcomes and course outcomes mapping. So we'll just understand what are the outcomes that are available, are written for this microcontroller and embedded system laboratory. So there are basically 4 course outcomes. The first one is very general: develop and test assembly language programs using ARM7 TDMI/LPC2148. So once you are able to, so if you know the instruction set thoroughly, you can write any ARM assembly language program and execute it using the key IDE. Second course outcome is develop and test assembly language programs using ARM instruction set for various applications. You can make use of arrays, functions, recursions in order to write an assembly program. That too using ARM instruction set. So this has to be done using ARM7 TDMI. You have to execute them, test them using ARM7 TDMI/LPC2148 device. The third one is develop ARM assembly language program using ARM instruction set to access and control different devices like stepper motor, DC motor, ADC, and DAC. So these are the different peripheral devices that you are going to interface to the, some are inbuilt and some you have to externally interface to the ARM evaluation board. And fourth course outcome is develop assembly language programs using ARM instruction set to access and control. Actually, this is keyboard, keypad, UART, LED, and 7-segment display. So there are 8 interfacing, 8 devices that you are supposed to interface and communicate with, make them communicate with the ARM processor. So these are the different peripheral devices: stepper motor, DC motor, ADC, and DAC. Along with that, you are supposed to interface keypad, UART. UART is internally available, ADC is internally available, it is inbuilt. But a stepper motor and DC motor as well as DAC, you are supposed to interface to the, externally connect to the evaluation board. The keypad is inbuilt again, UART is inbuilt, LED is inbuilt, 7-segment display, these are all inbuilt. But some of them you have to externally interface to the microcontroller. So let us not worry about the mapping, justification, and all those stuff. So it is the job of the teacher to do this mapping and justification. So all of you know about the course outcomes, program specific outcomes, vision and mission of our department, vision and mission of our college. So having, I think, hopefully you are aware of all these outcomes, right from vision, mission, program outcomes, course outcomes, program educational objectives, program specific outcomes. So all of these terminologies are aware, you are aware of all of them, hoping that let us understand what are the ARM instruction set available in the instruction set of, what are the instructions available in the instruction set of the ARM processor. So these are some of the instructions that you are repeatedly using them. The first one, it is in the alphabetical order. Hopefully you can see them. Let me make it, let me zoom it a little bit. Is it visible? Hope it is visible. So it's just a list of the instructions available in the instruction set. The first one is ADC, add with carry. So if you are doing some multi-byte addition, multi-word addition, then you have to make use of this add with carry, because my resultant, if the resultant has to be correct, I have to consider the carry. I should also take into account the carry. And if you are doing a single byte or single word addition operation, then it is simply add instruction. And it is a logical and. So for all these you need 2 operands. So those 2 operands have to be present in 2 different registers, general purpose registers. And there is one instruction called as BAL, unconditional branch and link. So BAL is branch and link. You are not checking for any condition here. You also have something called as just B. The mnemonic is B. B is branch. If I have some suffix with B, then it is a conditional branch instruction. If I can have BNE, BE, BZ, BNZ, BNG. So all these are conditional branch instructions. BIC is a bit clear instruction. Bit clear. So we'll be looking at that. It's a logical instruction. We'll take examples for all these, and we'll at the end of the before ending winding up the lab session, I will just show you a small fragment, code fragment of how a program, ARM assembly program gets executed. Any doubts so far? I have only discussed the syllabus. I have only discussed the course outcomes. So I have not yet come to the actual lab programs. Before going to the lab programs, we need to understand the instructions, right? So that's why I'm discussing some of the instructions that are repeatedly used in the program. So these are some of the instructions that are repeatedly used. So BL, I will just give you an overview of just one line explanation of what each instruction does. So BLAL is unconditional branch and link, branch and link. This is also unconditional branch, but this is unconditional branch and link. CMP is compare two numbers. UR is exclusive operation, exclusive OR operation. LDM is load multiple registers. LDR is load a register. Load an entire 32-bit data into a 32-bit register. So there is a provision in ARM assembly instruction set, ARM instruction set, where you can load only a byte of data into register. So whenever I am loading a byte of data, since the registers are all 32 bits in length, only the lower order 8 bits will be loaded with the 8-bit data. So LDRB is load register only a byte of data. MLA is multiply and accumulate. This is basically for the DSP operations. MOV is move. MRS is move from general register to SPSR, or this is basically program status register. Move from general purpose register to status register, and MSR is the reverse operation. Move from status register to move from status register to general purpose register, and move MSR is nothing but the reverse operation. So you are basically transferring the data between register and SPSR or CPSR. And MUL is the first program makes use of this MUL instruction. MUL is basically to multiply two numbers, two 32-bit numbers or two 16-bit numbers also you can multiply. Move N is if I want to move the ones complement of a number to the destination register, I can always make use of this MVN. ORR is logical, or RSB is reverse subtraction. So we'll be understanding the difference between just subtraction and reverse subtraction later. RSC is reverse subtract with carry. SBC is subtract with carry. SMLAL is signed multiplication. S stands for signed multiplication. MLA is LAL is long multiplication, signed long multiplication. MULL, this is for multiplication of signed numbers. This is for long integers. This is for just the we'll see the difference between these two. STM is store multiple. STR is store register. The entire 32-bit of data from the register is transferred to the memory location. STRB is if you want to store only a byte of data to memory location, there is a provision for the STRB is used to store the byte of data, specifically byte of data. SW is software interrupt. SWP is swap word value. Swap byte value is SWP. TEQ is test equivalence of two numbers. TST is just to test two numbers, and this is for unsigned multiplication. So these are some of the commonly used instructions in the instruction set of ARM. So let us take up one by one. So whatever is required for today's, I will show you how to multiply two numbers. Then you can try out by loading the software into your laptops and see how the results get stored in the memory as well as in the registers. Any doubts so far? We are not using GBA emulator, but let us understand. Is anybody any doubts so far? Okay. So we'll move on. We'll understand one by one in not in very much detail. We'll understand whatever is required for execution of a simple program. We'll understand. Some basics are required. So we'll go one by one, and finally we'll try to execute a simple program. And also I will show you how to multiply to 16-bit numbers. So there are registers R0 to R14 which can be used as general purpose, program counter and CPSR. So these are the registers that are available for a user to program. So only R0 to R14 can be used for programming, and PC cannot be used because it's a program counter. CPSR can be only read if the processor is in the user mode. If the processor is in the system is in the privileged mode or in the system mode, then user can actually perform a read write operation on the CPSR. So instruction set will define the operations that can change the state. So when we talk about the memory system, so what do you mean by memory? Memory is a linear array of bytes arranged from 0 to 2 to the power of 32 minus 1. So there are 2 to the power of 32 minus 1 memory locations, because the number of address lines are 32 bits. So you can always have number of addressable locations as 2 power 32. Since the address starts from 0, the last location would be 2 power 32 minus 1. So all the addresses are in hexadecimal. So you can see this suffix 0x stands for hexadecimal addresses. And since it is a 32-bit address, 8 digits are used to 8 hexadecimal digits are used to represent the 32-bit address, right? So address starts from 0, next 0, 1, 0, 2. It is a sequential linear array of bytes, and each memory location you will be able to store only 1 byte of data. It is byte addressable. So for every byte an address is assigned. So that's why it is called as byte addressable memory location. So bytes are addressed from 0 to 2 power 32 minus 1. So you have different sizes of the data. One is word. Word is nothing but a 32-bit data. Half word is 16-bit data, and byte is 8 bits of data. So you know what is the size of a byte. What is half word here? With respect to ARM, in ARM processor it is 16 bits. So in other processors it is different. Half word may be only 8 bit. In yet a third processor, a half word may be 16 bit or a 32 bit. Word here for an ARM standard processor, it is 32 bits. And you know what is little endian? There are two ways in which the multi bytes of data can be stored. if the lower byte is stored in the lower memory address and higher byte in the higher memory address, then that type of byte ordering is used is called as little endian, which is used in ARM memory also. While storing the data, multi bytes of data, it uses little endian. But there are some processors which makes use of big endian, which is just the opposite. So the way in which the data gets stored is just the reverse. So least significant byte will have the highest address. Word address is 0x000 and the value that is stored. So if I want to access 32 bits, then how do you access 00, 10, 20, 30? So these are the numbers. So if the first byte, that is the MS byte, is stored in the lowest memory address, that is 000, and the LS byte is stored in the last address, that is 003, because 4 locations are required to store 32 bits of data, each location 8 bits. So if I want to store 32 bits of data, I need 4 memory locations. So if I want to store this number 00, 10, 20, 30, so 00 is 1 byte, 10 is a second byte, and 20 is the third byte, and 30 is the last byte, that is the least significant byte. So how are these numbers, how is this value stored? 00 in the first location, 10 in the second location, 20 in the third location, 30 in the last location. So if it is storing like this, then we call it as a big endian byte ordering. And little endian is 30 stored in the first location. At 000 memory address, you have 30 stored. 001 memory location, 20 is stored, and 20 is stored in the 20 is stored here, 30 is stored in the first location, and 10 is stored in the third location, that is 002, and 003 you are storing 00. So this is how it is stored in the memory location. So the way in which the multi-byte data is stored, based on that you call it as either big endian or little endian. And ARM processor makes use of the little endian byte ordering. So this is and the programmer ARM programmer model is R0 to R14. These are the general purpose registers, and PC is the program counter, so which cannot be used for any purpose. And this is the CPSR, NZ, Q. These are the different flags that indicates the status of an arithmetic or logical operation. And these are the modes in which this indicates 0 to 4, bit number 0 to 4 indicates the mode of operation of the processor. So it could be any of the 7 modes. If one among the 7 mode, one of the modes is called as non-privileged mode, which is the user mode, and the remaining 6 modes are privileged modes. And IFT are the IF are corresponding to this corresponds to the interrupt and fast interrupt request masking. So if you are enabling this, then fast interrupt request can be masked. If you are enabling bit number 7, then interrupt request can be masked. T is, if it is equal to 1, it is executing the 16-bit instructions. So that means to say the processor is in the thumb mode. So these are the instruction set. Let us not look into the details of all this. We'll move on. Now, these are the features of ARM as already discussed. Load store architecture is also called as load store architecture because the only way in which the memory can be accessed is by making use of the load and store instruction, and 3 address instructions because we are making use of 2 registers to hold the source operands, 1 register to hold the destination operand. So that's why it is called as a 3 address instruction. Conditional execution of every instruction. Possible to load or store multiple registers at once. By making use of LDM and STM, it is possible to store and load and store multiple registers using a single instruction. So that is the power of processor. So you need not repeatedly execute the load instruction so as to store multiple registers or load multiple registers. Using a single load instruction, LDM instruction, it is possible to load multiple registers at once. And next one is it's possible to combine and shift ALU, possible to combine shift and ALU operations in a single instruction. That means to say it is making use of barrel shifting. That is pre-processing is done before ALU operation is performed. So what are the instructions that are available in the instruction set? Data processing, data movement, and flow control. These are the three types of instructions available in the instruction set of ARM processor. So what are these data processing? So they are nothing but move instruction, arithmetic, logical, comparison, multiply instructions. These are nothing but the data processing instructions. And most data processing instructions can process one of their operands using barrel shifter. As I told you, there are basically two operands given to arithmetic logic unit. One is Rn. This is one register which holds one of the operands. Rm is a register which holds the second operand. That second operand goes to the barrel shifter, and the resultant of the barrel shifter is given as input to the arithmetic logical unit, which is taken as the second operand. And there are some general rules that you have to follow. What are those rules? All the operands are 32 bits in length, even if they are less in size. The size of the data is less than 32 bit, that will be sign extended and will be loaded into the general purpose registers. So any operand coming from registers or literals are considered to be 32 bit. And if the resultant you obtain, if it is a 32 bit, it is placed in a register. If you are not specifying any memory location, until unless you use store instruction, it will be held in a general purpose register. And 3 address format is used. So this is these are some of the general rules you need to follow. Next is, let us see how to make use of this move instruction. Move, this is optional, this is conditional. CC is nothing but conditional. Yes, this is also optional. The angle brackets indicates you can optionally make use of this. You can skip this. I can just simply make use of MOV so as to transfer from source to destination, transfer the data or copy the data from source register to destination register. So it is only possible to copy from one register to another. It cannot be used to transfer from memory to register or from register to memory. So for that we have load and store instructions to transfer, copy between memory and general purpose register. Now, what do you how do you make use of this move? MOV CS. So what do you mean by MOV CS? MOV is move instruction. CS is move only if the carry flag is set. So this is corresponding to carry. If the carry flag is set, then only you perform a move operation. Only from where are you moving from? Where are you copying the data? From register R1 to R0. So when is this done? When is a copy operation done? Only if the carry flag is set, then only you are performing a data transfer from register. So R1 is the source and R0 is the destination. Basically it is opcode, destination, comma, source 1, comma, source 2. So since move operation requires only two operands, first one is the destination operand and the second one is the source operand. So you are moving, copying the data from the source to the destination. Move CS R0, R1. The meaning of this is you are moving or copying the contents of register R1. The entire 32 bits present in register R1 is copied into register R0 only if the carry flag is set. If the carry is reset, then this instruction never gets executed. So that is the meaning of move CS. And move S R0, #0. So what do you mean by this? Move S. So you are moving. What is this #0? The source operand is a immediate value. So immediate value hash indicates it's a immediate value. 0 is the value that you are copying into register R0. So what is that you are doing? Move only. So conditional move is done. So only if Z flag is 1, the Z flag, the 0 flag is set, and if the negative flag is 0, only then you move this 0 to register R0. Copy 0 value to register R0. So here the source is not a register, instead it is a immediate value. Destination obviously has to be a register. So the destination here is R0. Suppose if Z flag is reset, then this never gets executed. So if Z flag is set, then only if Z flag is set and negative flag is reset, then only this data transfer happens. So that is how conditional move instructions can be used. So almost all the ARM instructions have a conditional field which allows it to be executed conditionally. Move CS R0, R1. So as I told, this was discussed in the theory class. Carry set, equal, overflow set, greater than or equal to, plus, HI. If it is plus, then only move. If it is higher than, then only move. Higher or same, then only move. Carry, clear, then only if the carry is clear, then only you move, do a move operation. Not equal, if the two operands are not equal, then only you perform a move operation. So let me zoom it a bit. So these are some of the conditions that are that can be used as suffix with the move instruction based on the condition. If the condition is true, then only move instruction gets executed. So that is the one of the unique features of ARM instructions. Instruction set. Now, let us take two examples, two kinds of move instruction. One is move, and another one is move negated value. So, what do you mean by MOV? You simply copy a 32-bit value into the destination register. So, example for this move is move R0, R2. So, MOV R0, R2 means you. This is the source operand. R2 is having some 32-bit value that you are simply copying into register R0. MVN is copying the complemented value of R2 into R0. So here negation of R2 contents is copied to register R0. So that is the difference between MOV and MVN. So move a 32-bit value into register. So N is the value that you are copying into the destination. R is nothing but destination. Here also N is nothing but the value that you are copying to. So this could be a register or it could be an immediate value. So let us understand what actually gets copied. So initially, let us say before executing this move instruction, let us consider it as R0 and R2. R0 here is 5, R7 here is 8. Suppose if I say move